Okay, this week we're going to start with moving the air around, wind, and how that impacts the weather. We've talked about temperatures, we've talked about moisture, we've talked about pressure, all things that contribute to setting up forces that actually cause the air to move. So, what are some of those forces? That's what control the speed and direction of wind. Oh, yeah, one interesting thing is wind. We've talked about every other variable in meteorology pretty much, but wind is one that has two quantities. We have the speed it blows and the direction it's blowing from. So that is something significantly different about the wind. When you talk about wind, you want to know where it's coming from and how strong it is. So, and that is basically just the local motion of air. Uh, what is a force? Well, force is something that pushes or pulls an object. And air is an object. It has air parcels, as we've talked about. It has groupings of air. So you can push and pull on them. And it has both a vector, what we call magnitude and direction of that push and pull. So that is a force. Think about it with your car. When you're moving your car forward, there's something pushing it. Tire rotation, causing them to move the car forward. That's a force. Otherwise, that car would be sitting in your garage, parked, or in your driveway. When it goes around the corner, how does it hang in that corner? Why doesn't it just go straight all the time? Well, there's a combination of forces working on your car to keep it moving in the direction you want it to go. The same is happening with air. So when we talk about a force, we're talking about mass. We know that air has mass because we've talked about density, and with it, the mass of air. So the more it weighs in a way, the more mass there is. And an acceleration, that is a change in speed. When you push the gas pedal down in your car, you're accelerating your car. The same thing happens. If you dropped an object from the sky, gravity is going to accelerate that object down towards the ground at a certain rate. It's going to continue picking up speed if nothing else works on it. So those are all accelerations. And each one of them, all these forces work together to move the air around. So let's start with the basics. Pressure gradient is by far the main force working. The closer the lines together on looking at a pressure isobar map or contours and heights maps, it means there's a tight gradient of density, really, between two areas. And air is always trying to go from high pressure to low pressure. So it's going to want to get rid of that low pressure. So the more the lines are, think about going down a steep slope. If you were walking up a hill, you would have topography lines there, which would show the steepness of the hill. Well, isobars in this case, or contours on an upper level map, are that exact same thing. So they're showing the steepness of the slope. The steeper the slope, the faster the wind. So another force, centripetal force. That's what keeps your car on the road when you're going around the corner. And also, in this case, it shows you with the string holding tight to like a slingshot or whatever, rotating around. It is always acting towards the center to hold that object in a circular motion. Actually, if you look at the Earth rotating around the sun, there's centripetal force acting on the Earth in a way because the Earth is rotating around the sun. Guess what? The Earth rotates, so there must be a centripetal force acting on you to help keep you on the Earth as well, rotating in a circle. So this is a pretty common force, but it always is shown by something that is happening to keep you in the circular orbit. It's not independent force. So there's tension on this string. All of a sudden, if you were to cut that string and let that object go straight, centripetal force stops. There's no centripetal force at that time. But there is, like I say, on Earth, with the fact that we rotate, there is a centripetal force, be it weak compared to gravity, that actually must be there holding you onto the Earth, along with gravity. Coriolis force is the weirdest of all forces. The Earth rotates. We all know that. And the Earth is at the top of the poles, doesn't rotate hardly at all, right? Because it 24 hours, that little circle there by the top of the pole, you can walk around it. But at the equator, 24,000 miles around, you're moving about 1,000 miles an hour for the Earth. So the Earth is rotating much faster. A point at the equator is going to move a lot further than a point up at the North Pole. That change in distance is causing a force called Coriolis. That is an effect that happens to the air. In the northern hemisphere, it causes the air to turn to the right, and you can see it here illustrated. And here you can see the deflection in the southern hemisphere. Everything turns to the left. So if you were to change hemispheres, guess what? If you were a great pool player, you would need to take this into account because you're pushing a ball along a surface. In northern hemisphere, that ball is going to have a slight tendency to turn to the right. Might make you miss your shot, depending on whether you're at the North Pole or at the equator where it's left. However, maybe you go to the southern hemisphere. Again, that is impacting your shot as a pool player. Friction is another force. Think about it. If you try to push something along the ground, a rock or whatever, just pushing a flat rock against the flat ground, that's hard if it's a big rock. If you roll it, it moves a little easier. So all that is friction. And airflow. Air is moving against air. There's viscosity or fluid friction. So eddies form. Irregular motion develops. Friction is very, very complicated with things like turbulence. When you're flying an aircraft, all of a sudden you start bouncing all over the place. Some of that is turbulence. And that is because of the air causing this friction within its own layers. So the boundary layer is where the main area of friction is. That's down close to the Earth, maybe within 3,000 feet, maybe 5,000 feet, depending on a given day, maybe even only 500 feet some days. But it's a minor force, but it does change the direction of motion. So add it to the collection of forces you're learning about. Gravity. Gravity pulls everything downward to the Earth. So the further away up in the atmosphere you are, it's still going to get pulled back down towards the Earth, and it's accelerating at a speed of 9.8 meters per second. It always acts downward, so anything moving horizontal is not impacted by gravity. And because we're on a rotation of the Earth, like I said, centripetal force is the second component of gravity on Earth. So there are two components to gravity. And here's your listing of forces. Each one has its own impact and can explain why the air is moving in a certain direction, why you have wind. So let's just look at vertical air motions. Air pressure always decreases with altitude. We know that. We've learned it in pressure, looking at it, and it decreases pretty doggone quickly. The pressure gradient is much greater in the vertical than any pressure gradient you're ever going to find, even in looking at into a tornado. The pressure gradient is still greater in the vertical. So that should be immediately pushing all the air upwards and out away from the Earth, but it doesn't. Gravity holds it in. And because of that, there's a balance that's reached called hydrostatic equilibrium, where gravity is pulling the air down, pressure gradient is pushing the air up, but that air parcel is not moving. That's hydrostatic equilibrium. Now, if a gust of air were to push that air parcel up, it moves at a constant velocity if it's maintaining hydrostatic equilibrium. Say it hit a mountain. it would move upward at a constant velocity. Say it came down the other side of the mountain, it would move down at a constant velocity. So that is one of the keys with hydrostatic equilibrium. Air particles can move up or down, but they don't accelerate. We try to keep things simple in meteorology sometimes. There is several different types of wind motion we can talk about. Say you want to talk about just straight line winds, winds that are moving right along with the isobars, parallel to them, not across them at all. How does that happen? Well, you have a pressure gradient pushing from the high pressure to the low pressure, and you have a Coriolis effect pushing to the right on that force. So you wind up where they become balanced, you have straight wind. You have two forces in balance, and the wind will move not towards the low or towards the high, it just moves right parallel to isobars. Now, if you're going around low pressure systems or high pressure systems, there's another component. Centripetal force. We've talked about that, making it circular. So that is offsetting and constantly changing with itself around the circle. So it's an unbalanced force. So that's what's causing it to go in circular motions around highs and low pressures. And the same would hold with low pressure. Friction. So in the lowest part of the atmosphere, you're going to get this in critical thinking question, what changes? What are the forces within the lowest by the ground? Friction is one of them. That's the key difference. If you didn't have friction, you would be either in gradient wind force or geostrophic force. But because you add friction, friction reduces the speed of the air. So if it's reducing the speed of the air, well, then the Coriolis force is not as strong. So if the Coriolis force is not as strong, that's going to change the air motion. So instead of moving parallel around the high pressure, because of that change, we move towards low pressure and away from high pressure at an angle. Not directly in towards low, not directly away from a high, but at an angle. That's what friction does. That's why you see this in the very lowest part of the atmosphere. That's why winds in the low pressure system are converging, because they're being pulled into the center of the low and they're diverging in a high. And you can see that image here where the winds are blowing in towards the center of a low pressure. There's a continuity to wind. So if I move winds apart at the ground, air from above it's going to have to come down to fill it. So the air is going to be sinking. Otherwise, there would be a vacuum, and since we don't have vacuums in the atmosphere, so air has to move both. And that's why we just talked about in high pressures, the air is always moving away from the center of the high. The air sinks. Well, air sinks, we know it warms. We know it gets drier. That's why you have nice weather in high pressures typically. Low pressure, we know we have convergence of wind. Oh yeah, so that's in a low pressure. The wind's going to be pushed, can't go into the ground, so it's going to tend to go upwards. So it goes upwards, there must be some kind of horizontal divergence to allow it up there then. So that's where your low pressures are going to be. These are key concepts that we're going to explore over and over in the next several chapters here. So finally, the continuity of wind. Think about it. We've talked about friction. Take Lake Erie. If you have a wind over Lake Erie is smooth relative to the ground around it. So the air is going to be picking up speed as it's coming across Lake Erie. It's going to hit that ground. What's going to happen? It's going to get slowed down by friction. So if it's getting slowed down, the wind's piling into it from across the lake, what's going to happen? You're having convergence. The air has got to start rising. So now on the other side of the lake, say we have a north wind coming into the lake and you're on the north side of Lake Erie. Well, it's been slowed by the ground all along. Now it hits the lake and says, hey man, I can move. So it does. It takes off and moves quickly. So you wind up with divergence, the air sinks. So that's why you have, with the wind direction of northwest winds on Lake Erie, you're going to have clouds on the south side of the lake and clearing on the north side of the lake. So with that, let's just take a quick peek here. I wanted to show you a weather map this morning. This weather map is low pressure off the east coast, off the Carolinas. And this is a surface low pressure. Look at the winds blowing inward towards the low, especially right here, right to almost in towards it. And if I move up, there's nice high pressure to my north. I'm moving out of the way from the high pressure. So I'm moving away from the high towards the low. Tighter pressure gradient, the stronger the wind. Oh yeah, look at the winds, much stronger over water, less friction. So everything you've just learned, we've just applied to the atmosphere and can come up with reasons why the wind is such. So with that, let's take a look aloft. If we wanted to look at geostrophic winds, we have a pretty tight contour gradient out here. Here's your geostrophic wind parallel to the contours. And the strongest winds right around here, moving along. Lesser gradient, weaker wind, but it's still parallel to the contours. So it is going with the circles here. Whether it have a low pressure here, if it was more pronounced, it would be more circular, and centripetal force would be involved. Interestingly, when you look at a sounding, you can look at winds. And this is a sounding from Morehead City, North Carolina. We looked at that low that was off the coast, and you can see that low is generating a north wind at the surface and east winds and southeast winds just above it for about, roughly about 15,000 feet. So it's pulling moisture in off the Atlantic in that area, in that height. And then above that, the winds begin to change. So the actual low pressure at the surface is changing. We have low pressure, but it's further to the west and it's shifting the wind direction. So you can actually see wind shifting, as we've talked about before, in the depth of the atmosphere. So hope you get something out of this today, and now you've got a little bit of reasoning why. All because of the pressure changes, which we know come from density and temperature. So you've learned some things here. You're putting it all together to move air around. The air that's hitting you in the face, why is it moving in that direction now? Now you have some reasons behind that. Let me know if you have any questions about this.